Hello all, I want to welcome you to today's class, and today will be the second part of module 3. This is going to be a short lecture on the periodicity of elements, and we start. I have my quote here. I won't talk much about this quote, but it just says the essence of education lies in drawing out the very best that is in us. I want you to think over it, and most of my quotes is just to motivate you to know that nobody can be a barrier to your success. And let's get into it. Our learning objective today is just one single learning objective that one learning objective is what we're going to be tackling today, which is recognizing the trends in a periodic table and use them to make predictions of selected properties of elements. And those trends we're going to be looking at will include the metallic trend, the atomic size, and then the ionization energy. So let's get to it. So periodic trends. You see, the periodic table trends are specific patterns in the periodic table that we recognize either when we go across the period or when we go either across. You see, when we go across the period, of course, usually means from right to left or from left to right horizontally, or when we go down the group. If we go down the group, usually we go either up or down the group vertically. Those are those particular properties or patterns we see when we do this. Of course, if you're going across the group, you find out that electrons are being added successively from one element to another. And if you go down the group, you've noticed that shells are being added successively as you go down the group. And those properties we're going to be looking at today are going to be number one, we're going to look at the metallic property. We're going to see that atomic radii or the size, the ionization energy, and then the electronegativity will be covered much later. We'll not talk about this for now. It will be covered much later in another module. Okay, let's get to it. Of course, a metallic property, if you look at the periodic table, okay, let me take you to my periodic table here. See, this same periodic table I had in the first part of this module that shows the periodic table as classified between metals and non-metals. You see, if you look at this, you find out that now the metals are located to the left side of the periodic table, whereas the non-metals are located to the right side. Of course, in between the boundary is where we find the metal. What does that tell you? It tells you that ordinarily, from what you see now, if you begin to go left to the periodic table this way, that tells you that the metallic character should increase. That's exactly what this means. And if you're going to go across, maybe to the right, the metallic property should decrease. Let's look at the trend. You see, if you look at this trend, now elements in the same period will become, or the periodic table will become less metallic if we're going from left to right. That makes sense. You see, because like I said earlier, from this towards this side is where we have the non-metals. And you expect that the trend is going to decrease as you're going from left to right across the period. However, if you're going down the group, the metallic property increases. And part of the reason why the metallic property increases is because the size of as you go down the group, remember this is shell 1 or period 1. Remember the shells, I told you earlier, the shells represent the period. So basically, as you're going down the group, as we see from here, you find out that you're adding more shells, and the electrons that are in the outermost shells are far apart, and that tells you that metal could even easily react more by releasing its electrons. So for us to know this, what is the trend? Now, if we go from left to right across the period, the metallic trend decreases, and as we go down the group, the metallic trend does what? Increases. Okay, let's go to the next trend. If you look at this again, try to marry that with what we have here in the periodic table, and you're going to understand that fact that by location of these guys to the left, the metals to the left of the periodic table, that is actually what makes this thing very logical and coherent. Then the next one we're going to be seeing will be the size of the atom. Of course, the size of the atom is simply measures the radius of an atom, and the best way we can figure out the radius of an atom is by looking at the structure I just put up here. So if you look at this, we can assume that these are two hydrogen atoms. Now the two closest hydrogen atoms that are very closest to each other can be measured. If we can measure the distance from one of them to the distance from another one, this will constitute the diameter of this. Now, if we get the diameter and divide it by 2, of course, that will be the radius. Of course, ordinarily we understand that the radius of a circle is just the distance from the center of the circle to the circumference of that circle. So that is akin to what we have here. So it is just the measure of the size of the atom. So it is the distance from, of course, the center of the atom or the nucleus of the atom to the atomose shell. Of course, now it has to be the atomose shell of that atom, because most shells, of course, apart from hydrogen and helium, other atoms will have more than one shell in the periodic table. So we should look at this as a mathematical radius. So it's very important if we look at this as a mathematical radius. That helps to look at it and understand it that way. So going to the actual trend, what is the trend? The atomic radius decreases as we go across the group. As we go across the group from left to right. You see, as we're going from left, from this point, this is my left. As I'm going from my left towards my right, the atomic radius does what? Decreases. Why does it decrease? It decreases because the effective nuclear charge increases. Now, the effective nuclear charge represents the number of protons. You see, as if you're going from here to here, if you look at it, and if you're going from left to right, let's see an example. You're going from hydrogen, of course, that is located there, to helium. You're going from lithium. You're going to beryllium. You're going to boron. You're going to carbon, nitrogen, oxygen, fluorine, neon. I don't want to keep writing them. But what am I trying to tell you? What I'm trying to say is this, is that as you're going from left to right, you are increasing the atom one by one. You are increasing the number of protons or the number of electrons as well, one by one. And as that is happening, remember, the atom, of course, we try to see the atom as a centrally placed nucleus where you have both the protons. Of course, remember, we have the protons and we have the neutrons as well. Let me keep the neutrons out like that. Now, outside here, basically, in this cloud, this is supposed to be a cloud, we have the electrons that are floating around as a cloud. Now, what does that mean? What it means is that, of course, the proton is positively charged and this is negatively charged. There's an attraction between the two. So if you increase the number of attraction by increasing the number of protons, what are you doing? You will also increase the attraction between the shell and the nucleus. And if that attraction is increased, what happens? The size of the atom does what? Shrinks. And hence, the radius decreases. So what are we trying to say? Saying that if you're adding valence electrons, you're adding protons. What happens? That the protons, the nuclear charge, you should remember the proton is responsible for that pull. It pulls the electrons inside, shrinks the size of that atom, and hence what happens? It reduces the size of this atom. Then what happens as you go down the group? Now, as you go down the group, of course, the size of the atom, the orbital size, which is the general size of the atom, increases in going down the group. What happens? Remember, as you're going down the group again, the period, of course, represents the what? The period, of course, represents the shell. So as you're going down the group, you're going down, this is period 1, period 2, period 3, period 4, 5, 6, down. So as you're going, you're adding shell. So what it means, an atom that has one shell and the one that has two shells, which one is going to be bigger? Of course, the one that has two shells. So the more shell you add, the bigger the size of the atom. And the bigger the size of the atom, of course, the bigger the radius of the atom. So that is why as you go down the group, the atomic size or radius increases. So if you look at this animation shows you the calculated values of this atomic size. So if you look at it, it is actually coherent from my explanation in the previous page. If you look at this, as I'm going from, let's look at this group now, group 1, from lithium to sodium to potassium, you see the size increases successively. And if you look at these numbers, these numbers are measured in picometers. These numbers are measured in picometers. You find out that this increases as well. Now let's go across. As you're going across the period, look at this. You're going from lithium. Lithium is bigger than beryllium. Beryllium is bigger than boron. Boron is bigger than carbon. Carbon is bigger than nitrogen. As you're going across the group, the size decreases. And the reason why the size decreases is because the nuclear pull by the proton in the nucleus is dragging the cloud into itself and hence reducing the size of the atom. So the next trend we're going to be looking at is the ionization energy. You see, what is ionization energy? Ionization energy is the energy required to remove an electron from a gaseous atom. Of course, the electron you are removing, most likely the easiest electron to remove will be the electron in the outermost shell most times. The electron that is in the outermost shell will be, of course, the most loosely bound one, and that is the one you easily remove. So generally, the trend increase. Now, I like telling students that the trend in ionization energy is opposite of the trend in atomic size. So I like to see that I can say that atomic size is opposite of the ionization energy. And that makes sense. The trend is opposite of each other. So we're looking at the trends now, remember. So the trend of each is the opposite of each other. Remember when we talked about the trend, we said if we're going from left to right across the period, the atomic size decreases. In this case, it increases. It's just the opposite of each other. And it is almost the same reason why this happens. So if you look at it, if you're going from this to this, the the ionization energy increases. And if you're going from top to bottom of the periodic table, it decreases. Why? That makes sense. Remember when we said earlier, when I talked about atomic size, you see, as you're going from left to right, more protons are being added and more electrons are being added to the same shell of an electron. What is happening? The more protons you add, the more the attraction between the nucleus and the cloud, the electrons. And the more of this attraction, the stronger the bond between the nucleus and the electron at the outermost shell. Now, if you try to remove this electron, you're going to do quite a lot of work to remove it. So the work you do in trying to repel this electron is what actually defines the ionization energy of that atom. And that is the reason why it increases across the period. On the other hand, if you're going down the group, remember again, you're adding more shell. Going down the group means adding more shell. And the more shell you're adding, what happens? The electron that is at the outermost shell is actually very far apart. And because it's very far apart, it is weakly held by the nucleus. A little bit of work you do is going to rip it off, and hence the energy decreases as you go down the group. The explanation is on this page. So look at it. It says, while going down the period from left to right, the first ionization energy increases. So why does it increase? Electrons are added to the same shell, remember, or energy level. You're adding it to the same shell or energy level, and are generally strongly bound to the left, from left to right on the periodic table. Why? Due to the attraction between the protons and the electrons. This attraction gets strong if you have them on the same shell and you add more electron, because you're increasing the number of protons, there will be increase in the number of neutrons, and the charge is going to be more. Now, what about when you're going down the group from top to bottom of the periodic table? The energy does what? Decreases. Why? Because the electrons that you want to remove are actually very far from the nucleus. And because they are very far from the nucleus, it takes less energy to remove them. And because it takes less energy to remove them, the ionization energy will do what? Will reduce in this case. And that is the exact reason why as you go down the group, the ionization energy decreases, and as you go across the period, it increases. So let's do this problem. It says, which of the following has the largest atomic size? If you look at this now, it says which one has the largest atomic size? Now, the largest atomic size, if you look at the periodic table, I'm looking at mine now. Sodium is in group. Let's look at sodium. See, okay, let's just take a look at it. Let's not preempt the answer. If you look at this now, aluminum is in period 3. This is period 3. Beryllium is period 2. Let's see. Sodium is period 3. And then magnesium is in what? Period what? See magnesium here. Magnesium is also in period what? Period 3. Now, so we know it cannot be this one that is in period 2, so we take this one up. Now, among these ones that are in period 3, where are they placed? Remember, As you're going this way, the size does what? Decreases. As you're going this way, the size does what? Increases. What that simply tells you is that anyone that is far apart is going to decrease. So if you look at these three ones, now if you look at these three we have here, you find out that aluminum is actually very far in the periodic table. You have aluminum at some point in this place. Aluminum is somewhere along this place. And then you have your, let's say if this is our hydrogen, this is lithium, beryllium, this is sodium, this is magnesium. Now, what you see here, you find out that aluminum is actually very far this way. Therefore, this is going to really be small because the size would have decreased. Now, if you look at these two, which one is further to the right? The one further to the right will have a lesser size, and therefore, this is actually further to the right than this, and therefore, sodium is going to be the largest, and that is why we have sodium to be the answer. That you're going to use your periodic table to figure this out when you see this kind of problem. Again, it says arrange the following elements: beryllium, fluorine, titanium, aluminum, carbon, and cesium in increasing order of atomic size. What it means, you're going to rearrange them from lowest to highest. Now, when you look at this figure, now the first thing you need to do at this students, first of all, look at the number of shells. Now, if you look at the number of shells, you find out, what do you see first? You find out that your fluorine and your carbon are located where? They're located in the second shell. So they're going to be the smallest. But which is going to be the smallest? The one that is furthest to the right is going to be the smallest in what? Atomic size. And which one is that? It's going to be the fluorine. So fluorine, of course, will be less than which one again? Of course, carbon is in that same shell, shell 2. It's going to be smaller, is in period 2. Then if we jump from that period, which one is the next? Aluminum. If you look, so we've gotten this and this. Then aluminum, now if you look at aluminum is in period 3. And there's no other one in period 3. The next one close to it is titanium, and titanium is in period 4. So eventually, it got to be aluminum that will be the next one. Then after aluminum, what do we have next? We now have, if you look at that, next, we got 3 of these, we remaining 3. So we're left with beryllium, titanium, and this. If you look at beryllium and cesium, they're in period 6. So they ought to be bigger than, so no, beryllium, if you look at beryllium and cesium, sorry, they're in period 6. So they ought to be bigger than titanium. So titanium will be the next one. Then, we now can, these two that are in the same period, which one is furthest to the right? The one furthest to the right is what? The one furthest to the right between these two is beryllium. Because beryllium is number 56, cesium is number 55. And therefore, this one that is furthest to right must be smaller than the one that is to the left. Therefore, beryllium will follow, and then cesium will be the bigger. So this direction is actually increasing from lowest to highest. This is increasing order of atomic size from lowest to high. I usually advise students to use the less than sign for your arrangement from less, or from the lowest to the highest. Now it says arrange the following elements, the same type of elements, in increasing order of ionization energy. Remember what I told you earlier? I told you that the trend, I remember I wrote this, the trend in ionization energy is opposite of the trend in atomic size. So I usually advise students, just take your atomic size and change it since you have it already, because that exactly makes, so it is exact opposite. So what do you do? Take exactly what you have there, like what you have here, turn it on the other way, and that is exactly what you're going to have at this point. And that makes sense. So, because the one that is going to be the largest will be the one that is the topmost, and the one that is closer to the right. And that one has to be fluorine. So in this case, fluorine is going to be the biggest. And cesium, that is closest down to the left, will be the smallest. So here we're going to have cesium will be less than the one that is following beryllium. Beryllium will be less than titanium. Titanium is going to be less than aluminum. Aluminum will be less than carbon, and carbon will be less than fluorine. 1, 2, 3, 4, 5, 6. So we got it completely. All right, so this is the trend again. Like I said, this will be the increasing order of ionization energy, increasing order of ionization energy. So we're going to stop at this point. Like I said, this is a brief lecture on periodicity of elements. Thank you for listening once again. And if you have any questions, do not hesitate again to communicate me through the proper channels. Thank you for listening and have a wonderful day.